All right, let's get into it. If you've ever worked with object-oriented programming, you've definitely come across the word polymorphism. It sounds a little intimidating, right? But it's one of those core ideas, and today we're going to unpack it with some really straightforward examples. So let's start with a statement that I think we can all agree on. A bicycle is a vehicle. Simple enough. It fits into that bigger, more general category. It has things and behaviors that all vehicles share. This is what we call an is-a relationship. And it's a perfect way to start thinking about how object-oriented programming sees the world. Well, no, of course not. That would be ridiculous. A vehicle could be a car, a truck, a boat, you name it. And this right here, this simple little question, it gets to the absolute heart of what we're talking about today. The relationship, it only goes one way. You can always use a more specific thing, like our bicycle, anywhere you'd expect to see a more general thing, like a vehicle. But you can't go the other way around. And this really powerful concept, it has a name, polymorphism. It literally means many forms, and that's exactly what it is. It's what allows us to treat a bicycle just like a generic vehicle when we need to, without ever forgetting that deep down, it's still a bicycle with its own special qualities. This definition really nails it. It's all about being able to write code that deals with the general idea of something, like a vehicle, without needing to worry about the nitty-gritty details of whether it's a car, a race car, or a motorcycle. We're basically interacting with one single interface that can show up in many different forms. So how does this actually look when we're writing code? Well, the first big piece of the puzzle is something called method overriding. This is all about how different but related classes can hear the exact same command but respond in their own totally unique ways. Just think about it like this. You have a parent class that sets up a general ability. Then a child class comes along, inherits that ability, but decides to, well, redefine it. The child class basically says, hey, I see you have a way of doing this, but I've got my own, better way. That's overriding. A race car is a perfect example. It's a special kind of car, right? So they both have an accelerate method. But if you call that method on a regular car, you get, well, regular acceleration. But call that exact same method on a race car object, and whoa, you get a completely different, much more powerful result. Same command, totally different outcome, all based on what the object actually is. Okay, now let's switch gears a little to a related but very different concept, overloading. So if overriding is about different classes having their own version of a method, overloading is about a single class having multiple versions of a method. It's like one class that can wear many different hats. The key thing to remember here is that this is all happening inside one class. You can have several methods with the exact same name, and the program is smart enough to know which one you want to use based on the ingredients or parameters you give it. It's kind of like having a recipe called Make Cake that can give you a chocolate cake or a vanilla cake, depending on what you put in. And this fraction class is a fantastic example. Look at all the ways I can create a new fraction object. I can make one with no information, or just the top number, or with both the top and bottom numbers, or even by just giving it a string like 1/2. They're all called fraction, but the system just picks the right tool for the job based on what I provide. Super flexible. Now, this all feels pretty magical, doesn't it? But how does the program actually figure out which version of an overwritten method to call when the time comes? Well, the secret sauce behind all of this is a concept called late binding. The most important word here is runtime. This decision isn't locked in when you write and compile your code. Nope, it happens on the fly, while the program is actually running. The system literally waits until the very last possible second to figure out what kind of object it's really working with. Let's just walk through it. First, you declare a variable with a general type, something that can hold any kind of motor vehicle. Then, later, while your program is running, you assign a very specific race car object to that variable. Finally, when you call accelerate on that variable, the system doesn't care about the general motor vehicle type. It looks at the actual object sitting there, the race car, and runs that specific version of the method. Okay, so we've gone through the what and the how, but honestly, the most important question is, so what? Why does any of this matter? What's the real-world benefit of all this? The payoff is just huge. Because of polymorphism, our code becomes incredibly extensible. We can add a brand new motorcycle class into our system, and guess what? All the old code that knows how to handle vehicles just works with it. No changes needed. Think about the alternative. a massive, messy block of if-else statements checking every single object type. Polymorphism lets us avoid that nightmare and build systems that can grow and change without breaking. So, to wrap this all up, let's just think beyond the code for a second. Think about the word play. You can play a video game, you can play the guitar, you can play a part in a movie. It's one word, one interface, play, that means something different depending on the context. Polymorphism isn't just some abstract programming concept. It's a fundamental way we organize and make sense of the world around us.